Hi guys and girls, a video here on exponential modelling, which basically means coming up with equations and formulae and things like that that can be used to model an exponential scenario. So things like population, radioactivity, money investment, that kind of thing. Right, so anytime you're seeing anything referencing a population, it doesn't have to be human population obviously, investment, radioactivity, they're the kind of typical ones, but obviously there's loads more. Basically we have to create an equation to reflect what's happening within this population. Okay. I've got a couple of examples, one where it's an exponential growth, and that'll be a bacterial population, and one with an exponential decay, which I'm going to approach as radioactivity. So if we start with a bacterial population, okay, and we are given, so it is given by the number of bacteria is 5,000 times 2 to the 3t. T is hours. Yes, 3 is hours since the experiment began. In other words, it's doubling every hour. It doubles 3 times because you get 2 to the 3. Anyway, that'll become clear. So what is the initial population? And we're going to say, when does the population exceed 1 million? So what is the initial population? So the initial population is when t is 0. So t equals 0 gives us n is 5,000 times 2 to the 0. 2 to the 0 is 1, so it's just 5,000. We then ask, when is the population exceeding 1 million? I'm going to say first exceed, because obviously any time after it, it will exceed. So first exceed 1 million. Run out of space. Okay, so we know that 1 million has to be equal to 5,000 times 2 to the 3t. And we're going to try and solve it. So if we first off divide by 5,000, that will give me 200. And then I'm going to take logs. I'm going to go log to base 2. No, I'm just going to keep it as log. Yeah, just keep it as log. So log of 200, well, that's log base 10. Oh no, I need to do log base 2, don't I? Oh, sausage. The only way this is going to drop down... No. I'm way overthinking about this. Just log it, like you would do anything else. Okay, now drop your power down. So I get log 200 is 3t log 2. So what am I going to divide by? Divide by 3 log 2, so I get log 200 over 3 log 2 is t. I'm then going to shove that in a calculator. And that gives me 2.55 hours. So 3 significant figures. So anything over 2.55 hours. So that's 2 hours and about 30 minutes. That's 33 minutes. So any time after 2 hours and 33 minutes, the population of this bacteria will exceed 1 million bacteria. Okie dokie, next one. So this is going to be a decay. So we've got a substance, doesn't really matter what it is, has a mass, given as m equals a e to the negative 1.5 t. And the negative part is what tells you it's a decay. The initial mass, can't spell, the initial mass is 72 grams. And we want to find the rate of change at t being 7. Find the rate of change, or rate of decay, at t equals 7. Okay, so we know the initial value. We want the rate of decay. This is what the mass is. So the rate of decay is the derivative of the mass. So rate of decay is dm by dt. So if we... Oh, hang on. We need to find out what A is. I can do that in a minute. Oh, go away. Oh, why won't you go away? There we go. So the derivative of this is going to take the coefficient of t, so the negative 1.5, and drop it down the front. So we get negative 1.5a e to the negative 1.5t. So that's the rate of change. I just need to know what a and t are. So we know, what do we know? We know that when t is 0, m is 72. This is going to help me find out what a is. So 72 is a e to the 0. Okay, so a is 72. So dm by dt, so the rate of decay, is now, what's negative 1.5 times 72? 1.5 72s is 98? 108. So negative 108 e to the negative 1.5t. And we need to know the rate of change when t is 7. So when t equals 7, the rate of decay is e to the negative 1.5 times 7. And again, shoving that in a calculator, we get negative 0.00297 sig fig. Okay, so that means that it is decreasing, hence the negative, at 0.00297 grams per... Oh, do we know what t was in? We don't. That's because I've written an example and not written it in the actual question. t is in seconds. So this is losing grams per second. Ugh, rubber, come on. There we go. Oh, come on. There we go. Ha! Okay, that's basically it. You'll be given an equation. You use your what's called your initial boundary, or you might even be given a boundary partway through, but you'll know a pair of information. Sub that in to find any missing values, and then either solve it using logarithms if you need to find a particular time, or at a particular time you're just substituting in. It's not the most difficult thing in the world. It's a substitution question, just wound up in the guise of an exponential scenario. Anywho, hopefully that all made sense. See you later. Bye.